name is Ajay, and in this session, I'm going to talk about a feature store which we call Himalaya. This is built in Zeta, and it was built to solve a use case which prevents financial fraud. Little bit about Zeta before we see what Himalaya is. Zeta is a banking tech startup. It provides cloud native products to banks through which they can build all the core banking products. It also provides embedded banking tech for fintechs through which fintechs can build some customized products on top of core banking offerings. So in a way, it bridges the gap between banks and fintechs. We process over 1 million transactions and few billion events per day. This is going to be our agenda. We'll see Zeta's ML-based FRM system. FRM is nothing but fraud risk management system, which we use to prevent financial fraud. We'll look into what kind of problems are faced by ML engineers and how Himalaya solves those problems. We'll see what kind of features are supported by Himalaya. We'll deep dive into the Himalaya architecture and other complex pieces. We'll see how Yugabyte fits into the Himalaya ecosystem. And finally, what is the path ahead for Himalaya? Let's start with what it takes to build such a FRM system which can operate at our scale. So we need to, we need the ability to train the ML models on huge amount of historical data so that we can identify certain patterns. We should be able to serve those models in real-time path in order to calculate risk and hence determine whether this transaction is good or not. We should also be able to define some custom rules through which we can allow or deny a transaction. And we should be able to serve those models and run those rules in a very low latency manner so that the end user experience is not impacted. Given the rate at which digital payments are growing, we should be able to scale this system for a very high throughput. This is the conceptual architecture of FRM. So we have a number of data sources on the left-hand side. These data sources can compute features which are stored into feature store. So at this point of time, let me take the opportunity to introduce or to define what a feature is and what is a feature store. So feature is nothing but some sort of measurable attributes of any real world entity. So let's say account is a real world entity. So we may say that last X minutes of transactions count, or maybe the average transaction sum between 1 a.m. to 5 p.m. or 1 a.m. to 5 a.m. in last 7 days. These are some measurable attributes of an account. We could have some very simple key value pairs at account level like KYC status, something of that sort. These are also called features. So yeah, these are features, and then we use a store where we can kind of keep all those features. So that is called feature store. So coming back to our conceptual architecture, so we have the data sources through which we compute features. We store those features into feature store. We have ML models which can query the feature store, and for any incoming transaction, it can evaluate the risk and maybe come up with some risk score. We have custom rule engine which can again look into some incoming transaction, query feature store and determine the risk score. So any client of this FRM system can send the incoming transaction to FRM, and FRM system can execute ML models and rules to come up with a final score. So if we take the conceptual architecture which we just saw, and if we have to implement it, um, we can just outline what would be the problems which will be faced in general by the ML engineers. First thing, you need to transform all the raw data into features, which means typical data engineering exercise like setting up data ingestion pipelines, writing those queries which can do the aggregation, transformation, and whatnot to compute the features from raw data. Once you have computed the features, you need to find a store on some online store where you can store those features. And that store should be able to give you very low latency guarantee because you will be looking for those features in the online path when someone is kind of waiting for a transaction to happen. You also need analytics and segmentation support for your model training purpose, offline usage. We need monitoring of the complete infrastructure, and we should be able to emit all the business matrices like how stale the features are, or how many times we are serving null values, or something of that sort, right? And if we look into any organization, right, we have pretty much a lot of similar use cases, right? So we are solving the FRM use case. We also have recommendation use case where we kind of recommend something based on user transactions. And again, we are looking for some historical contextual data of a given account. Maybe what is the weekend spend of that user? What is the 3 month average balance for a given account? Same sort of things. Again, needed for a different purpose, but technically you have same things or same set of steps to be executed, like identifying data sources, setting up those ingestion pipelines, storing the data into online store, and so on, right? So it's like the repetitive work done by different teams in lack of some centralized infrastructure. So let me introduce Himalaya and also like call out that how it can solve all the problems which we saw in the previous slide. So Himalaya offers a centralized place to store all the curated features, right? Which means, if I have created something for FRM domain, and I feel that, this can be used for, let's say, a recommendation domain, then pretty much I can share this feature with the recommendation team, and this will be readily available for them without doing any piece of work. It provides easy to use DSL through which features and all the relevant entities can be registered into the system. We can define the queries with respect to how those features will be computed, and starting from data ingestion to how data will be stored, everything is encapsulated within Himalaya. So yeah, I mean, like you can just access those features in a very using the very low latency API in the online path, and everything is available for the Himalaya users in a kind of a ready-made manner. It supports composite index keys. So in addition to the entities which we have identified and on which we define features, I can have some complex composite keys also. For example, I may say that give me transaction count of a given account device and location combination for last 90 minutes. So all those things are very well supported here. We can also do point in time lookup of data for offline model training purpose. Himalaya is completely cloud native, so you can run it anywhere. Uh, it supports multi-tenancy and RBAC. This is the high-level flow of users who are using Himalaya. So they define the data sources, which could be stream or batch. They define entities which are identified by the entity IDs. For example, account can be identified by account ID, device can be identified by device ID. So all those entities are kind of defined in feature store, and then we register all the features, and we basically link those features to entities, and we also pass the secondary index keys, which are optional. I mean, you may or may not have secondary index keys at feature level. You also define the queries through which those features will be completed. And once we have defined all those things, the feature ingestion pipeline will kick in automatically. And data will start flowing into feature store. So you can access those features through the entity ID, and if you use any secondary index keys, yeah, you can pass those keys also. There are two high-level features which we support. First one is window-based feature, where we have some notion of time, like some transaction count happened between this period of time to that period of time, or maybe transaction sum between some timestamp, something of that sort. So any feature which has a notion of time, we call it window-based features. Non-window-based features are just key value pairs. Here, value can be a single object, or it can be a list of objects. So let's say if KYC status of an account is a feature, then this is a single object key value pair. I can have something like last 5 known locations of an account, which is an example of a list type of feature. Let's deep dive into the data model of window aggregate feature. It's a key value pair at high level. We use entity ID as the partition key, and the reason we do that, so that we can keep all the features of a given entity ID in one partition, and at the read time I can do a bulk read of all the features through a single node. We want to avoid that scatter and gather call. We use the composite key as clustering key, and feature ID as key. The value is a map of tumbling time windows, which are stored in a protobuf format. Because this map is ever growing, so we use TTL and keep expiring the stale entities. This is the read and write path. So let's say at 10:40, I'm looking for last 5 minutes of aggregates. I'll go into this map. I'll start from 10:35 and I'll go until 10:40. I'll get all the values and apply the aggregation function on top of it. If I'm looking for last 5 hours of data, I'll go to hourly map first. I'll start from, if my running hour is 10th, I'll start from 5th hour. I'll go until 9th hour. I'll aggregate these values. And on top of this, I'll add, the running hour data from minute map. So this is our read path. In the write path, let's say I got the feature value computed for 10:45 as some value. So I'll go to this map and I'll create a new entry here. If I get an update for this value, I'll update this map similarly. This is the high level architecture of Himalaya. So we have a feature registry component through which we define all the features, entities, queries, and anything which is relevant in the lifecycle of feature. We have streaming and batch ingestion pipelines which taps into the data sources. They compute the features and they store the features into the online store. The data syncs from online store to offline store. We have the API. So in the model serving path, we you know they call the API to fetch the data from online store. For the model training purpose, they access the offline store to get the data. This is the tech stack of Himalaya. For streaming ingestion, we use Flink and Kafka. For batch ingestion, we use Spark. Our online data store is built on top of Yugabyte, and in the upcoming slides, we will see why we picked up Yugabyte. We use S3 for offline data store and other offline stores like Blob, Azure Blob are something which we are evaluating currently. So when we were, doing the design of Himalaya, at that time we were doing extensive research of, what should be our online data store, which can serve our requirements. We listed our requirements as P0 and P1. We can see those requirements. So first thing was cloud agnostic because we operate on multiple clouds. So we didn't want anything which is just limited to one cloud offering. So we are looking for a cloud agnostic solution. We are looking for something which can scale horizontally. And I mean, yeah, we can't have something which is a single node solution and we just keep doing vertical scale. That model wouldn't fit for the scale at which we operate. So we needed something which can scale horizontally. ACID compliance was not relevant for feature store use case, but we are also evaluating a lot of transaction use cases, and for that purpose, we are looking for something which is ACID compliance. Uh, we needed high availability because we know how critical, or how sensitive financial world is. So we needed something which is highly available. Again, for the same purpose, we needed something which can be deployed in multi-AG and multi-region. Then disaster recovery, low maintenance, they are our other P0 requirements. These are our P1 requirements. So Postgres query layer, again, not relevant for feature store use case, but as I said that we were evaluating other transaction use case. And, in Zeta, most of the traditional workload is built using Postgres. So we're looking for something which is Postgres compliant. In Zeta, we have built pretty much everything around open source technologies, and we are a big fan of open source community. So we are looking for something which is open source and it has active community support. We needed automated backups. We needed CDC. Encryption, both at transit and rest, was required. And yeah, finally, we needed something which is cost efficient. Yeah, we had a lot of other pointers, to compare the databases. And I think this is just a trimmed version of it, something which could have fit into the real estate of this slide. But yeah, there were not many other pointers. There are just like some important things which I wanted to highlight. And if we look into this table, we can see that Yugabyte and CockroachDB, they are close competitors. Uh, Yugabyte offers everything in open source version, including encryption, and CDC, which was something we were not getting in Cockroach DB. We also ran YCSD benchmark just to get the confidence for our workload. So we simulated like 100 million records, each having 1 KB in size for different types of workloads, which we see here. And we benchmarked both Cockroach DB and Yugabyte for both interfaces. And as we can see that Yugabyte outperformed Cockroach DB for most of the workloads. So based on our research on different comparison pointers which we saw in the previous slide and the benchmark which we did, we kind of finalized on Yugabyte as our online data store. So yeah, this is the future or path ahead for Himalaya. We want to build a Python SDK, which is a wrapper around our XSR and registry API, so that it is more convenient for our ML and data engineer, the data science folks. We want to support more network protocols like gRPC. We are evaluating additional offline stores so that it is compatible with all the cloud providers. Currently, we have RBAC at high level, which we call namespace. That is a domain level separation of features. But we want to build RBAC at granular feature level. Finally, we want to make it open source. We strongly believe that this is a very common use case which a lot of companies are trying to solve, and we feel that we may minimize their time to market if they are investing in the same area. So we want to make it open source under Apache license. So yeah, that's all I have for today. Thanks a lot for joining today's session. Thank you.